Hello everyone, and welcome to AIM113, Advancing Physical AI. My name is Sean Kirby, and I'm a Principal Internet of Things and Robotics Architect in AWS Professional Services. And I'll be joined today by my colleagues Rishab from NVIDIA and Abhishek also from AWS. And we're going to be sharing some very exciting technologies with you here today. So we've got a fun-filled agenda taking you to the horizon of AI and beyond, as we look at the frontier for applying the amazing capabilities of artificial intelligence to the physical world. We'll start off giving you a survey of physical AI and a glimpse into the incredible future it promises. We'll then examine the significant challenges of executing physical AI and take a look at how NVIDIA and AWS are working to help roboticists and technologists everywhere to meet these challenges with the right tools in the cloud. I'll then hand to Rishab, who will dive deep into NVIDIA Omniverse and Isaac Lab. And then Abhishek will give you a demo of these technologies in action and leave you with some tips and best practices so that you can be part of this revolution for physical AI. So first off, what do we mean by physical AI? Well, simply put, physical AI is the integration of artificial intelligence and the physical world. To date, a lot of the focus has been on robotics, but it really applies to everything from autonomous vehicles to industrial manipulators and even robot-run infrastructure like factories and warehouses. Amazon Robin is one example of a robot that moves billions of packages each day and has to have considerable physical intelligence for handling the great variety of these packages, everything from soft, flexible bubble wrap packs to long rectangular boxes whose contents can shift unexpectedly. And it's got to do all of this with the utmost quality without damaging anything, and also at warp speed. Robots like the Animal from Anybotics are being trained to execute a parkour, which is a difficult feat even for human athletes. And on the very forefront, NVIDIA's Groot is a robotic physical intelligence development platform for creating physical AI on humanoid robots. And these robots, with their form factor, are ideally suited for a myriad of tasks in a world that's created for human beings. Well, perhaps most excitingly, while large language models have given rise to the big bang of generative AI, physical AI really still has yet to have its big bang moment. But with the tools and approaches that we're going to share with you here today, you can be part of this explosion. Well, okay, physical AI really sounds fun and exciting, but what are some of the practical applications? Well, one benefit, as we've already seen with Amazon Robin, is productivity and efficiency. These can be dramatically increased. Physical AI can be trained not only to take an often boring and repetitive task like sorting packages and improve it, but it can do so at warp speed and with the quality control and consistency necessary to offer same-day delivery on millions of different items, all with free shipping. But it can also be trained to execute dangerous tasks in hazardous areas like mines or disaster sites, keeping human workers from harm's way. And with the same kinds of transformer models that give generative AI its amazing capability, physical robots and machines with multimodal models can be trained to achieve general artificial intelligence and solve a wide variety of different problems, even things that they've never seen before. So more specifically, physical AI has applications and benefits across industries. As dexterity improves, robots can take on a greater variety of manufacturing tasks and serve as cobots, collaborating with human beings on everything from assembly to quality inspection. Companies like Amazon are employing physical AI systems such as autonomous mobile robots and robotic arms to streamline logistics operations. These systems can navigate warehouses, avoiding obstacles, pick and pack items, and optimize inventory management. And physical AI has many applications in healthcare, including minimally invasive robots that are being trained to do everything from thread needles to sew perfect stitches. They can also be used as assistants to aid people with disabilities or sense and respond to patient needs for progressive physical therapy. They're also being used in healthcare to clean and disinfect and to serve as a nursing assistant and for remote patient monitoring when immediate assistance from a human nurse is not available. Now, robots are being used in physical AI as well in agriculture for tasks like precision farming, involving everything from crop monitoring to autonomous harvesting and even livestock management. John Deere's See and Spray solution, for example, can save 2/3 of the amount of herbicide required by pinpointing the weeds that need to be shot. And it doesn't stop there. Physical AI is used in the exploration of everything from the insides of pipelines to the deep ocean and even nuclear power plants. So how is development of physical AI possible to do all these amazing things? Well, the key is simulation. And that's because developing advanced robotic systems on physical hardware is just way too time-consuming, too expensive, and even potentially dangerous. But in a simulated world, we can train hundreds or even thousands of robots simultaneously, each executing at speeds many times what they would run at in the real physical world. And we can test in a nearly infinite variety of situations by synthesizing realistic environments with endless variation. All this amounts to much faster product development and much, much more thorough test coverage and higher quality physical AI. There are numerous examples where simulation is already having an impact across various different industries. Multiply Labs, for example, enables small batch personalized medicine with custom pill packs that are created by a robotic arm. And through simulation, they were able to shave a whole year off their product development lifecycle. And they also were able to accelerate from taking weeks for new releases to being able to provide multiple thoroughly tested releases every day of their solution. Now, similarly, Miso Robotics, maker of robots for applications like food services, uses simulation to speed up their development life cycles and test things like software longevity and the customer impact of new features almost daily. And iRobot increased the amount of testing for their updates and new product releases by 20-fold. And they're able to do this in a matter of hours rather than days. Now, right here, actually in our own physical AI program at Amazon Robotics, we've manufactured and deployed the world's largest fleet of mobile industrial robots. And the newest member of our fleet, which is called the Proteus, is Amazon's first fully autonomous robot. And Proteus' function is to lift and move bins of items and packages within fulfillment centers. And the team used NVIDIA Omniverse, we're going to be talking a lot to you about that today, to create realistic simulations that accelerate deployments across fulfillment centers. One particular application involves reading fiducial markers for the robot to determine its location. And using simulation in Omniverse reduced the time for development of that feature from months to just a few days. And it doesn't stop there. We're also using simulation to speed the development of next-generation multi-sensor fusion-based applications for autonomous operation of whole fleets of Proteus robots. So, problem solved and on with the big bang of physical AI, right? Well, unfortunately, not so fast. Physical AI remains an enormous challenge. Just setting up a training and simulation environment can take months. You've got to do everything from procuring the hardware to installing the operating system and the whole technology stack, from simulation frameworks and models to simulators and training scripts, not to mention configuring evaluation utilities and visualization tools and many other items. All this involved a lot of very steep learning curves, and you often wrestle with consistency across installations if you have a large organization geographically distributed, and you want to have your teams be able to build on each other's results and use standardized tools. Now, not only that, but Training and even fine-tuning some of these physical AI models for sophisticated tasks is a very time-consuming and resource-intensive task. And so unless you have a really large physical AI program with lots of different projects, you're probably going to have to over-provision. So your hardware is not going to be optimally utilized for a longer period of time. And even worse, you could face periods of contention that will slow down your product development life cycles and delay your time to market with new solutions. So all of these seem like a lot of really daunting challenges, but there is hope. And in today's session in particular, we're going to show you how the NVIDIA Omniverse platform on the AWS cloud can solve these challenges and unlock the vast potential of physical AI. By using curated, ready-to-go containers with all you need for realistic simulation and physically accurate models set to deploy on AWS batch and scale across multiple nodes, each with multiple NVIDIA GPUs, each capable in turn of simulating thousands of robots across hundreds of different virtual environments, all at warp speed, you can be part of this physical AI revolution. So, now to dive into the amazing NVIDIA Omniverse tools, I'll hand over to my colleague Rishabh.
Thank you so much, Sean, for the quick introduction to physical AI and simulation. Hi, everyone. I'm Rishabh. I'm a technical marketing engineer with NVIDIA, and I focus primarily on the robotic simulation side of things. So I think if we traditionally look at robotics, it's always been a more complex problem. Like if you imagine robotics in traditional settings, for example, like maybe assembly line tasks in manufacturing warehouses or even pick-and-place operations. So even to the point where you get into robotics where you want a robot to do a certain task, it turns out to be pretty complex in terms of programming it to do that task. So this is what makes it challenging. And even when you are able to program it to do a certain task, it doesn't really scale across any different dimension. So what I mean by that is, suppose I have an industrial manipulator, a simple one right here, and it's going to do pick and place for a certain task, which is maybe related to assembly of a small sub-module. So what really happens over here is you need to program the robot to sort of understand what the task exactly is. It's going to move to that particular location, pick that object up, and put it somewhere else. So what happens if the path changes? What happens if the task changes? Well, it's not that straightforward anymore. You need to get the robot into downtime, you need to reprogram it again, and you need to test and validate it for it to be able to do the tasks again in that new environment. And this is why robotics also has been traditionally challenging. And even if you get a robot to be able to do certain things, like it doesn't really scale across different environments as well in terms of like, supposing I'm using an AMR which is navigating. An AMR is an autonomous mobile robot which is meant to navigate from point A to point B. So can I use that same navigation algorithm for a quadruped, which might be like a legged robot or a humanoid? So there's so many parts and pieces which need to change in that overall process, and then getting a data set and creating like that entire pipeline for training that robot and testing it turns out to be complicated. So you've got so many pieces here and there which need to be tweaked and adjusted, and all of them change depending on what sort of task you're looking at and what sort of robots you could be looking at. So robot learning really looks to help and simplify this process, in which like newer advancements in reinforcement learning and imitation learning are some things which we'll be looking at in the next slides as well, which enable robots to learn to do tasks better. But it turns out that this is complex to do in the real world. And that is because if you're already familiar with generative AI models, right, large language models, they're trained on vast amounts of data, like internet scale data. And these models are then able to intelligently understand that data and provide valuable insights. You can extract summaries and you can have creative prompts going into the model. So they really interact with your data which you're providing from the input side of things in the space. You get tokens as output. It doesn't really have any implications in the real world. Like it doesn't move an object in the real world, for example. So that's how generative AI is a little different from physical AI, because you don't really have the aspect of actuating a robot or actually getting something done in the real world, so which turns out to be more challenging. So you can collect a data set for sure, and doing that with a robot in the real world turns out to be challenging. So imagine if you're familiar with reinforcement learning, it's basically where a robot learns by mistakes to do a simple task. So what I mean by that is, suppose I want a robot to pick up a cube in front which is on the table. So I have a manipulator right here, and I've got a cube placed right here in front of me. So initially the robot really doesn't know like what is the cube, what is the environment, it has no clue. So it's going to do random actions, and you're going to reward certain actions, which is then going to cause the robot to slowly learn how to do that particular task. So this can be tedious in the real world. Imagine like if I want to teach a quadruped to walk, it's going to fall down initially because it really doesn't know what's happening. So it's going to fall down, it's going to do random things. And doing that in the real world with a super expensive robot doesn't really make sense. So this is where simulation really comes into the picture for the whole robotics workflow. And before we understand what Isaac Sim is, we will take a look at NVIDIA Omniverse, the platform over which all of this has been built. Omniverse is a platform for APIs, SDKs, and services for developers to integrate OpenUSD and RTX rendering technologies into their current software development work cycles. So OpenUSD is the format in which worlds are represented in Omniverse, virtual worlds, and it's been developed by Pixar, and it's open source, and this is the foundational layer over which Isaac Sim is built. So Isaac Sim is a reference application for developing, training, testing robots in a physically accurate and photorealistic environment. And that turns out to be important. Like both of those components in robotics are important because you would want the physically accurate part in simulation to hold true, because if I'm training something in simulation for maybe a quadruped to walk, I would hope that it's also going to work in the real world. So this is what is referred to as the sim to real problem in robotics, where you do something in simulation and then you try to do that same task in the real world on the basis of something you learned in simulation. But it's not as straightforward as it sounds, because as we know, the real world is very complex, and you've got noise, you've got random things happening in the environment around the robot, and that's what makes it more challenging. So if I'm a roboticist, what is the first thing I would need to simulate a robot? Well, I would need to represent the robot in a certain format, right? So maybe I've modeled my robot in a 3D modeling software like SolidWorks or CATIA. So I've represented the robot, and now I want to simulate it. So how do I get it into Isaac Sim? So we've got a variety of extensions and importers which enable you to bring these data types into Isaac Sim. And this is over USD. So as soon as you get your assets into simulation, it is being converted into USD for you. So there are other types of extensions also available, including like the URDF extension, which allows you to import URDF files. So if you're already familiar with ROS and you've been a part of like the robotics community and sort of have an understanding of the workflow over there, that's a popular format for representing robots with like all the geometry of the robots, all the joints, all the sensors, all of that is encoded in that format. You can bring it over straight into Isaac Sim, and now you've got the physical representation for that robot in your simulated world. So I've gotten to the first point where you've got your robot into Isaac Sim, and sensors are also important for robots, right? So how does the robot perceive the environment around it? And also maybe it needs to monitor some of the things internally for like the robot states itself. So for perceiving the environment around it, you can use cameras, LiDARs, radars, or ultrasonic sensors. All of these are already available with Isaac Sim. So once you've imported your robot, you can straight away add these sensors onto your robot, and you're good to actually simulate the robot now. So simulating the robot would also involve interfacing with the robot. So how do you control that simulated robot? So that is straightforward through Python scripting. You can script entire workflows where you bring in the robot, for example, into Isaac Sim. You set up the sensors, you set up the entire simulation scene, and just use Python to basically control the robot and run your software stack for that particular robot. Or if you're familiar with ROS and you've already written your robot software stack with ROS, you can use the ROS1 or ROS2 bridge extensions with Isaac Sim, which will enable you to use your entire ROS software stack and control that simulated robot inside the Isaac Sim world. And another important aspect which Isaac Sim also enables is synthetic data generation. And imagine if you're training maybe a perception-based model and you're running into data problems, which is popular in general. You would want to be able to generate synthetic data from a photorealistic environment, and because in simulation you already have access to ground truth, you know what is there in the scene, and you can set up cameras in the scene how as per your requirement and generate that entire data, and that will be completely annotated. So generate that data, plug it into your training pipeline straight away, and you can train your models better. So now we've looked at what Omniverse was in terms of like the most foundational layer over which Isaac Sim was built, so that you can have a simulation platform for robotics, and having a simulator which is able to simulate a robot is obviously a very important piece over here. But the other important aspect is also the task itself in terms of like the learning environment. And what I mean by that is when we looked at the example for pick and place, you could have any robot, you could have any situation. So the task itself is like something which you need to define for your particular use case, and it could be different for different robots and environments. So that is where Isaac Lab comes into the picture, and it's an open source modular learning framework, particularly a robot learning framework, which is built on top of NVIDIA Isaac Sim, and can interface easily with robot learning libraries so that you can have robots learn better in terms of tasks, and that's which are completely simulated within Isaac Sim world. So what are the three important pieces for robot learning? I think we've hinted to all of them as we've covered a few important foundational concepts while we made it till here. The first one is the data generator and the renderer, and the second one is the task design environment itself. We'll be taking a deeper look in terms of what exactly this means. And the third one is the robot learning framework itself, which is where you would have the agent, which is basically the robot brain, which is going to learn something about how to do a particular task. So Isaac Sim is going to serve the purpose for actually simulating your robot, and you've got access to the ground truth from there directly. So access to camera data, access to internal state of the robot, contact sensors, and all of that. All of that is done through Isaac Sim. And you've got your robot learning frameworks, which actually help your robot to learn a particular task, and have got models encoded for doing all of that. So Isaac Lab is that important middle layer which connects a simulated robot to the agent, or like the brain of the robot, so that you can have like tasks set up, and for doing a particular task you would need observations, rewards, and a few other things which we'll be taking a look at in the next coming slides. But at a higher level, you would need a simulator which is going to be able to simulate the robot so that you get access to the ground truth data. Then you need the robot brain as well, which is going to be able to learn from the data which is coming in, and the important interface in between which actually enables you to define all the tasks and all the other parameters which are needed for that robot learning entire workflow is Isaac Lab. So Isaac Lab comes pre-baked with a variety of environments, robot embodiments, and assets. In terms of the environments, you can have tasks ranging for pick and place, locomotion for quadrupeds, navigation, multi-agent reinforcement learning. So they come directly available with Isaac Sim. It's straightforward as going to the standalone examples and hitting enter, and you can have a simple task in front of you which can have a robot learn to do a particular thing. So we also looked at robot embodiments where you can understand how to bring a robot into Isaac Sim, and that is actually represented in the right format. So that enables you to bring your own robots, or you could also use the embodiments which are already available. So they include humanoids, quadrupeds, AMRs. All of them are already pre-baked, so they're already in the USD format. But if you want to bring your own, you can use the importers and the extensions which enable you to bring in your own assets. And sensors also play an important role even in the robot learning world. And you've got access to regular cameras, RGBD-based cameras. You've got raycasters as well as height scanners, which could be important for quadruped locomotion, for example, where the quadruped needs to understand how far off it is from the ground while it is trying to learn how to walk. All of this comes pre-baked with Isaac Lab, so you can directly set them up in terms of your task, and you should be able to use them straight away. So like we discussed earlier, an important aspect for you to actually be able to do something in the real world using these robots is that what they learn in simulation should also be transferable to the real world. And this is what we refer to as sim to real in the robotics world. And accurate physics simulation plays a very crucial role over here in all of this. So on the animation playing on your left, for example, Isaac Sim is provided, is backed by NVIDIA physics engine. So that is handling all the physics simulation which comes into your simulation platform right there. And this is important because like once you train something in simulation, you will be able to do it in the real world as well on that corresponding robot. And like we saw earlier, Isaac Lab connects to reinforcement learning libraries and even imitation library frameworks as well, and plays that important role as the middleware. And scaling this is also very important because you can do all of this on a single GPU, and maybe you have thousands of environments with thousands of robots running a certain task, which could be like quadruped learning how to walk. But you can also do this across multiple GPUs and multiple nodes, and that really accelerates the whole training process because like your time to market goes down drastically. Instead of training for weeks, you can have a policy trained within a few hours. So we looked at what robot learning is, and reinforcement learning is one particular important aspect in the whole robot learning workflow in general. So Isaac Lab supports 2 workflows with reinforcement learning, and we'll be looking at them in more detail over here. But to even understand what reinforcement learning is, I think I briefly described it. It's basically that you have an agent, which is maybe your robot brain, which is learning how to do a particular task in an environment. That could be a simulated environment, or it could be a real world environment. So it's basically learning how to do something in simulation for our use case. So the environment provides the agent with an observation. So let's take an example of pick and place. It's as straightforward. I've got a tabletop right here, and I've got a robot arm, and I want to maybe pick a cube. So the observation is basically what you would want your robot brain to understand. So it could be maybe the position of the cube is important for pick and place. That's my guess. So I would want to know the position. I would also want to know the state of the robot itself. So a robot has many joints. I would want to know where it is located in that simulated world. So I need access to the robot itself in terms of its joints. I also need access to where the cube is placed. And I could have maybe a camera setup, maybe that is detecting the cube. So an observation is basically any of the important parameters which you would want your policy to be able to understand, and that's what you're going to train it on. So you have an observation which comes in from your simulator. That observation is now passed into your policy. Your policy could be a deep neural network, which is your robot brain in this case, which is being trained to do a certain task. And the output of that policy is going to be an action. So I got in maybe the joint position information, I got the position of the cube. The action should be that the robot needs to move in a particular direction. So it could move anywhere initially when the policy has no clue because it's not learned anything yet. It doesn't really know what to do. So, and you want to reward this policy on the basis of what it does. So if, for example, this is my cube right here and this is the robot, if the first observation from my environment passed through the policy and the action I got is I start to move towards the cube, this is probably good because that is what I want to do. If I want to do pick and place, I want to move to the cube first. So instead of moving maybe to a random direction, it's now moving towards the cube. So that's positive reward. So this is how the reinforcement learning cycle at a high level continues, where the robot gets the environment provides an observation. Observation goes through your agent, which is the robot brain. The agent then gives an action to that particular environment back. Your robot does that task and it gets a reward. If it does it successfully, you would terminate training, and if it doesn't, then you keep going through the loop. So we came across a couple of key terms over here in terms of like observations, rewards, and the termination as well for this. So there are two ways which you could actually accomplish this whole workflow with Isaac Lab. The first one being that it's completely inside one single class. So I want full control over stepping through simulation, and I'm going to do everything inside just one class. So I'm going to calculate the observations, I'm going to apply the actions, I'm going to get the rewards. All of this is handled only by one entity itself. So that is the direct workflow. You've got your simulated robot, one entity is handling everything for the environment side of things, and all that information goes over to the agent. But if I'm looking to do maybe a more complex task, or if I'm actually tweaking many parameters inside this whole workflow in general, I would want more finer grain control. Maybe I want to change the reward a little bit. Maybe I want to change the observation space a little. So that is where you could utilize the manager-based workflow, because you can set up different configurations for each of those individual important aspects which you want to look at in simulation, and that will be orchestrated completely within Isaac Lab, and that will be passed on to the learning agent. So both of them have their own sets of pros and cons. Manager-based is really where you can tweak maybe like hyperparameters and a lot of the other things while you're getting like the robot learning application running, and it's more plug and play, it's more modular. Whereas for the direct workflow, it gives you more fine-grained control and it's efficient, but it might be like a lot of code because it's all going to be placed in one complete class. So you can select any one depending on what your use case and application looks like. So one of the use cases we have with Isaac Lab is we were able to train a policy. So the one which you see on the left is the Spot robot within Isaac Lab environment, and you can spawn thousands of robots in those environments, and you're going to train them to learn to walk, so basically locomotion. And once they're able to do that, you would want to transfer this to a real robot, right? Because the end goal for all of this is that whatever you do in simulation, you want to be able to do in the real world as well. So transferring that policy towards the real world is an important piece over here. And this is again the sim to real paradigm which we referred to earlier. And in this case, we were able to get a zero-shot transfer. So what I mean by that is there was no fine-tuning for the model when I had to actually deploy it on the robot. So as the robot learned to walk in Isaac Lab, the brain of that robot was able to transfer directly onto the real robot. So I didn't have to get more data from the real world and tweak the model parameters here and there, maybe fine-tune it. There was nothing. So it's zero-shot sim to real transfer, and once you've trained that policy in simulation, you could have done it maybe on a single GPU, or if you had access to a multi-GPU and multi-node setup, you could have done it there too. That trained policy can be deployed directly to the real robot, and that can walk as well directly. A few of the ecosystem adoption use cases which we've had is Fourier is one of them. So they've had the use case for getting a humanoid robot which is lying down on the ground be able to learn to stand up by itself. So that is an interesting use case which Isaac Lab also powers, and also related to grasping of objects for the humanoid in general. Galbot has been able to generate vast amounts of synthetic data and train grasping models on the basis of that. And Swiss Smile, which is the one on the right, is a more interesting design where it's a quadruped, but it's like wheeled. So instead of, it's got more complex dynamics, and they've been using Isaac Lab extensively for training and evaluating the policies. I'm now going to hand it off to Abhishek, who's going to walk us through how we can do all of this in the cloud on a multi-GPU and multi-node setup, and you'll be able to run all of this with AWS. Thank you.
Thanks, Rishabh. Hi, everyone. I'm Abhishek Srivastava, Senior Solutions Architect at AWS. So before I go over and discuss the integration of NVIDIA Isaac Lab on AWS, let's cover some of the best practices in running simulation workload on cloud. These best practices you can run in any cloud or even on-prem. First, use containerizations. Container plays a really crucial roles in simulation project. Setting up a simulation environment is really challenging. It requires multiple dependencies, libraries, operating systems, and middlewares. Container helps to bring portability and consistency across platforms and machines. It helps you to accelerate the development timeline and create consistent outcome across robot training lifecycle. Next, choose right compute resources. Robotic simulations often require complex physics calculations, rendering, policy training, and reward calculations. Choosing right compute capacity including both CPU and GPU combined, is essential to ensure that there is no performance issue, as well as your training is not going through any kind of bottlenecks. Third, robotic simulations very often require a massive data processing, whether it is a high-fidelity simulation environment or synthetic data processing or storing the checkpoints during the robot training process. Using the optimized storage ensures that the data is being maintained without any details being lost. It will also help you to improve the performance. Fourth, many simulation projects can get benefited from parallel processing because it optimizes the compute capacities. It gives you a faster computations by distributing the workload across multiple nodes and multiple cores of GPU. Choosing a right compute resources with GPU capacity will help you accelerate the performance, as well as it will optimize the total time of training. Finally, last but not least, optimizing your cost. Frugal architecture is the core tenet of designing anything, any workload on AWS. That goes to simulation workload as well. Choosing a right balance between a compute capacity, performance, and the cost will help you stay within the budget, still meet all the critical non-functional requirements. So how can AWS help you follow these best practices we just discussed and run NVIDIA Isaac Lab on AWS? AWS offered breadth of services for developers and researchers to build end-to-end pipeline for simulation workload. So developers can more focus on fine-tuning their models and policy rather than managing the underlying infrastructure. Let's start with AWS Batch. AWS Batch offers fully managed batch computing capacity to run NVIDIA Isaac Lab at scale. So you can run hundreds of simulations jobs in parallel without being hassled through managing the underlying infrastructure. AWS Batch integrates with Elastic Container Service, ECS, to provide containerized environment for Isaac Lab. You can use on-demand or spot EC2 instance or go completely serverless using AWS Fargate to offer compute capacity. It offers dynamic scaling of compute resources to optimize the total cost of robot training. AWS Batch natively integrates with Elastic File System as well as Amazon S3 to offer durable and cloud-scale storage for training data sets, synthetic data, trained model, as well as the trained policies. Finally, CloudWatch integration helps you to observe and monitor the training performance and the final outcome throughout the robot learning process. Okay, so AWS Batch simplifies the process of running workload on AWS. Developers can focus more on fine-tuning their robot policies rather than managing the underlying infrastructure. Let's dive into steps of launching Isaac Lab using AWS Batch. The first one is to select the compute environment. And this is where you will select the EC2 instance powered by a wide range of NVIDIA GPU family, which is suitable for your own workload. In the second step, you will create the job definitions. This is where you provide various job parameters such as container details, launch commands, vCPU, or memories. In step 3, you will define the job queue. This is where the job resides until being processed. And finally, you will launch the Isaac Lab robot learning job using the job definition and the job queue you just created. AWS offers a largest selection of instances supporting simulation workload. customers very often ask me, what is the best instance type for running their own workload use cases? Unfortunately, there isn't one-size-fits-all solutions, but here is the guideline that is going to help you choose right compute resources for your own use case. Now, we will be more focusing on the EC2 instance powered by the current generation of NVIDIA GPUs. If you are running a training job in a complex simulation environment using multi-robot, where time to market is critical, G6E instance powered by NVIDIA L40S Tensor Core GPU will offer the best learning rate. If you are running a training job where cost is the biggest driver, G6 and G5 instance powered by NVIDIA L4 and A10G Tensor Core GPU will give you the most cost-effective solution. The key takeaway is identify your key objectives, whether it is a faster learning rate or cost, and run the benchmark to identify the best compute resource for your own workload. AWS Batch can also help you simplify the evaluation process of choosing the right compute resources. All right, I'm really excited to show you a quick demo of launching NVIDIA Isaac Lab on AWS. All right. So there are a few steps involved. First, we will package NVIDIA Isaac Lab repository and Isaac Sim latest container together in a custom Docker image. And that's what we are doing. We cloned the repository locally, and then we packaged that with latest NVIDIA Isaac Sim container. Once the container is created, and for this demo, we are using Isaac Lab reinvent demo as the container name. You can see that the containers are created. The second step is to go to Elastic Container Registry, ECR repository, and create a placeholder repo to house your Isaac Lab custom image. All right, you go to the console, and you will have all the step-by-step launch command to push the custom image back onto ECR repository. So step one, we will authenticate ourselves. Once the client is authenticated to ECR repository, step two, we'll go ahead and tag the image which just created. All right. Once the tagging is complete, we'll just go ahead finally and push the Docker image back to ECR repository. Now, traditionally, this process takes 10 to 15 minutes, depending upon your network bandwidth and the size of the image. We will just fast forward this demo to the point where the image is already transferred. Yes, so image upload is complete. You go back to the ECR repo, and you see the image is available. Once this is done, we will move forward and set up the AWS batch. So the step one is to create compute environment. We will choose EC2 instance for this demo. Enter the compute environment name. This is where you will select the role, which will allow the compute resources to communicate to various services like Amazon S3, EFS, or any other services you need. We will select G6E instance for this demo, which is powered by NVIDIA latest L40S Tensor Core GPU. To provide the compute capacity, we'll not make any change in the additional configuration for now. Go ahead and select the network details. You will choose your VPC and a private subnet where the compute environment will be launched. All right, we'll go ahead and create the compute environment. Once the environment is valid, we will move forward with the next step of creating the job definition. All right? So for job definition, we'll select EC2 as our compute environment. We need to select multi-node processing. For this demo, we will be demonstrating the job being distributed across 2 different nodes. Enter the job definition name. Provide the execution time in seconds. In case if you want to provide the job attempts, we'll just go with default for now. Provide the total number of nodes. For this demo, we are going to go with 2 nodes. Select your EC2 instance type. For us, it's a G6E. And then add container details. For example, the image location for ECR repository. Once the container is launched, what would be the launch command? That's what will go under command. You can also add the vCPU memory and a GPU configuration for your own container. We would like to speed up the process, so we added a good memory, 16 vCPU, 1 GPU. In case if you have various parameters, runtime parameters, you can pass through the environment variables. The way we package Isaac Lab on AWS is we configured various of these parameters so you can easily go ahead and change that one. For example, task will identify the exact robot policy that you are training for your robot learning process. All right. The socket is going to be an ENI for internode communications. You can accept the NVIDIA EULA and a privacy statement from the environment variable. Provide the total number of epochs to train the job. And then finally, add the total number of GPUs per job. OK. We'll move forward. You can add the shared memory for your container. We will be using the exact same memory as what we given in the for the primary. And go ahead and create job environment. All right. So once this is created, we will go to the final phase, which is creating the job queue. We'll select EC2 as our compute capacity. We will add the name for the job queue, choose the compute resources we just created, and go ahead, create the job queue. All right. So at this moment, our AWS batch setup is ready to launch the Isaac Lab robot training job for Spot. We'll provide the job name, select the job definition we just created, choose the job queue. You will have options to override all of these parameters runtime. For now, we will just go ahead, choose default, and launch the Isaac Lab reinforcement learning job. All right, so once the job is in starting state, go ahead under Nodes tab, and you will see both the servers, both the EC2 instance, which we configured, is launching one by one to offer the compute capacity for the job. The job has completed because it's just 10 epochs, and then you can go to the CloudWatch log and monitor various training properties, such as the learning rate in terms of frame per second, total time for the training, total number of epochs. And also you can see that the location where the trained policy is set. Now, all of these you can configure and change into your own, based on your own use case. For now, we will just go ahead with the default location and launch Isaac Lab environment with the trained policy. And as you see, our fully trained Spot is right now simulating freely in the simulation environment without any issue. All right, here is an exciting announcement. We have a trained Spot robot at NVIDIA booth on Expo floor. Feel free to stop by to see the sim-to-real aspect of this demo, how we transferred this fully trained model into the physical robot, and how the physical robot mimics the exact what you see here in the simulation environment. So please do check out at NVIDIA booth on Expo floor. So let's summarize everything we discussed in today's session and review why you will use AWS to run Isaac Lab reinforcement learning. By using Isaac Lab on AWS, you can accelerate robot learning in a high-fidelity, ultra-realistic simulation environment at cloud scale. You can run a concurrent jobs without being constrained by resource capacities. You can choose on-demand or a Spot instance or go serverless and choose the dynamic compute provisioning to optimize the cost of training. And finally, this solution is backed by broader AWS ecosystems that will help you build resilient and secure infrastructure. AWS and NVIDIA have collaborated since 2010 and continuously delivered large-scale, cost-effective, flexible, GPU-accelerated solution for our customers. The collaboration between NVIDIA and AWS is deeper and help our customer across every segment and industries. From our partnership at NVIDIA DGX Cloud to offer scalable AI platform for developers and researchers, to NVIDIA NIMS integration with services such as EC2, EKS, or SageMaker, to our work for NVIDIA Omniverse, Isaac Sim, Isaac Lab, full integration for simulation and graphics workload. Together, we have pushed the boundary of what is possible in the field of AI and simulation. Feel free to join us later this afternoon on our builder session MFG 319 to get the hands-on experience on running NVIDIA Isaac Lab on AWS. Thanks for joining our session today. Hope you enjoy the rest of the conference.